3, 2, 1. That's right, everyone. It is time for parametric and vector equation applications. I'm Mr. Fritz, and today I'm going to be your guide in these problems. Let's dive right into parametric and vector equation applications. Here I have an example of a parametric application problem. I have a particle. It's described in its position as p of x of t comma y of t. It moves such that I have these two parametric equations describing its horizontal and vertical displacement. And we're in positive time land and in seconds, distance or in meters. We want to do all this stuff. So let's jump right into this. For letter A, I want to find the initial position of P. Well, to think about that, that's kind of like saying, well, where is the xy coordinate when t equals 0? So in order to do that, I can just think about the point of x of 0 comma y of 0. And if you plug in 0 for an x of t, x of 0 is going to equal 2 minus 3 times 0. 2 minus, x of 0 will equal 2 minus 3 times 0, which is equal to 2. And y of 0 equals 2 times 0 plus 4, which is equal to 4. So the initial point of this particle is 2 comma 4. That is letter A, done. Let's take a look at letter B. What do we want to do for this one? We want to illustrate the initial part of the motion of P when t equals 0, 1, 2, and 3. So what I'm basically doing is kind of diagramming this motion. So let's actually draw kind of a set of axes here. And actually, I'm going to move these over. And it would be helpful if I kind of figure out where my particle is at t equals 0, 1, 2, and 3. And since I came up with this nifty method of finding my initial point, I'm going to use that same process as before. So let's find x of 0. We already found x of 0 and y of 0, but let's find x of 1, y of 1, x of 2, y of 2, x of 3, y of 3. That's going to give my x and y positions, for these given time values. So this is for letter B. We have x of 0 is equal to 2 and y of 0 equals 4. If I want to find what x of 1 is, I'm going to plug 1 in for t, and that'll be 2 minus 3, so that's a negative 1. And the y of 1 is going to equal 2 plus 4, so that's 6. And x of 2 equals, continuing this process, x of 2 equals negative 4, y of 2 equals 8, x of 3 equals negative 7, and y of 3 equals 10. So that's a whole bunch of points that I basically am finding in this particle. And it looks like I've run out of room. Once again, let's move these axes over here, and don't forget about the x and the y. So let's plot what I have here. These are a whole bunch of coordinates, right? So at time equals 0, I'm at 2, 4. So that's about 1, 2, 3, 4. So let's say that's here. And that's at time equals 0. Next coordinate will be negative 1, 6. So that's negative 1 and up a couple more. That's right here. That's time equals 1. Then I've got negative 4, 8. 1, 2, 3. I'm going up 1, 2. So that's about here. Time equals 2. And then finally, time equals 3 will be at negative 7, 10. So that is, give or take about here. Time equals 3. And what I'll do is I'll just kind of chart this. This is still a vector, so it's still moving, so I can't just connect these dots and be done with it. But I'm basically going to draw a line or a vector through, let's go this color here, through these points. All right, so my line's not perfect, but you can kind of see this vector is moving from here and it goes onward, and I've charted each of these 4 different time intervals. And that's really how you can kind of show where the time is on an XY graph, even though we don't have this third dimension visible. The last thing I want to do is I want to find the speed of P, and I think I might be able to squeeze that in right here. The speed of any object in motion is equal to the magnitude of the vector. Basically, in every second, I am moving to the left 3 and up 1. So overall, that speed is going to be what that full length of step is between this time and this time. So let's take the magnitude of my vector. The vector would be -3, since I'm going 3 left in the x direction, and 2, since I'm going up 2 in the y direction. So the speed is going to equal the square root of -3 squared plus 2 squared. And that's going to equal the square root of 13, and we are in meters per second. So there is our speed of the particle p. So here's another example just like it. 2 different parametric equations. Why don't you give this one a shot, pause the video, and resume when you're ready to see the answer. All right, so here's my answer for the U-try number 1. Hopefully it went all right. And I don't have these marked, but this is going to be t equals 0, 1, 2, and 3 seconds. So moving right along, let's talk about just the velocity vector of a moving object. So this is kind of like what we were talking about in the previous video, but in general we have this equation. And let's just kind of break this down into its parts, into its components, maybe you could say. This xy over here is basically it's a vector, it's a position vector. And specifically this is at time t. All right, so this equation is going to help you find the position at any certain time in motion. This next piece, this a1, a2, this is our initial position vector. So this is basically where our particle is beginning. And then finally, the last piece of the puzzle here, this is our velocity vector. And just like in the last video, I kind of made an analogy of slope-intercept form of a line, where you kind of have like a y equals mx plus b thing going on here, where you have a rate of change that's being multiplied by your time, and then you have this position. The only difference between this and your slope-intercept form is that this just has 2 variables, where before we were working with just 1 variable, rather than these vectors. And then I guess what I should say is we also get the speed of this particle, and as we said before, that's the magnitude of the velocity vector, or the square root of, in this case, b1 squared plus b2 squared. So all kinds of stuff we get from this equation, this velocity equation. So let's see another example here. I have this vector equation, and it's about the path of an object. T is in seconds, distance is in meters. Let's find the object's initial position. Once again, we are looking for when the time is 0. So we have the position xy, or the position vector, is given as 7, 5, plus time is 0, so this is 0 times 6, -8. And because we have 0 multiplied by this velocity vector, this doesn't mean anything. This goes away, it's at 0. So my position is going to be 7, 5. And this is be my position vector, 7, 5, but the position, the point, is 7, 5. So notice that this, we keep talking about position vectors and positions as coordinates. And let's just talk about the difference real quick. If I have the coordinate 7, 5, and I call this P, P is a position. It's at a position, it's at a point in this plane. The vector, position vector, is the vector as described from the origin to my position P. So this is a position vector. The vector is used just to describe displacement from the origin to a position. But really the answer I'm interested in this letter A is the position, not the position vector. So I want a point. All right, and then for letter B, I want to find the velocity vector of the object. And really that's no more complex than just pointing out the velocity vector. So this is 6, -8. And then that was easy. So let's talk about the speed. The speed then is going to be the magnitude of my velocity vector. So that's going to equal the square root of 6 squared plus -8 squared. And if you work out the math here, this works out to be 10 meters per second. So why don't you try this example? Very similar. I'm looking for the same three things. I've got a new equation. Give this problem a shot. All right, here is my answer for the next you try. Let's do another example, a little bit different still. Here I have I want to find a velocity vector. It's not given to me this time, of a speedboat, and it's moving parallel to negative 512, and I have a speed of 65 kilometers an hour. So I want a velocity vector. I'm given a vector that is parallel. So we're really thinking of this as the direction of my velocity vector. This vector itself is not the velocity vector, but it's in the same direction since it's parallel to my velocity. And then this whole speed, this is my magnitude. So I'm given a direction and a magnitude. I just have to find out how to make these things kind of work together to find the actual velocity vector of this speedboat. So if we say that the velocity vector is equal to some v sub x, v sub y, this is some vector, we know that it's equal to some scalar value k times the direction vector negative 512. Right? So if these things are parallel, as they should be, as given by the problem, then I really just have to find out what this k is and then multiply this direction vector by k, and then I'll have my velocity vector. So what can I do about this? Well, I mean, I know that the magnitude of this, the magnitude of my vector vx, vy should equal the magnitude of whatever k times negative 512 is. And actually, in general, like, you can't take the magnitude, or you can take the magnitude of a scalar value, but a scalar value is just itself. The size of 5 is 5. The size of 10 is 10. So really, this is the same thing as just some scalar times the magnitude of negative 512. And all of this, we're given the magnitude, is 65. So basically, this boils down to k times the magnitude of this vector, which is the square root of negative 5 squared plus 12 squared, is going to equal 65. So the magnitude of this should equal the magnitude of my velocity. This whole square root comes out to be 13, and that should equal 65. So if you do a little bit of algebra here, we find that k equals 5. So using that fact, we bring this right back here, and we say that the velocity vector must equal 5 times negative 512. What does this mean? This means that our velocity vector is negative 25, 60. That is the velocity vector of my speedboat. And you could check this. If you take 25 squared and 60 squared, you add them up, you take the square root of that, you should get 65. So it's a great way to kind of check how you did on this problem. So why don't you try this problem? It's a whole lot like what we just did. I've got a direction, I've got a magnitude. Try and find the velocity vector of this speedboat. All right, and here is my velocity vector. It's at 120 and negative 90. Let's take a break for this video, and when we come back, we're going to talk about constant velocity problems.